Okay, so let us say you have some data set, okay, and you want to split it into two subsets. Let's say one is a training set and the other is the uh, testing set. Okay, so how can we split the entire data into two sets? Okay, so let me right now create some data. Artificially, we can always work with the imported data soon. So we'll do that soon. But let's just create some data set. Okay, so of course you can actually use NumPy. Okay, to create arrays. Arrays are a way to store data, so let's do that. So I'm just creating an array called data underscore set. Okay, so np.array. Okay, and let's just put some numbers. Okay, okay, so let's say we have these four rows and four columns. Okay? Or maybe let's have one more. Okay, okay, so let's say we have this data set which has five rows and four columns. Okay, so let's just quickly check the shape. Okay, you can see it's five rows and four columns. So what we want to do is maybe we can just create a split. So first three rows are you can say the training set, and the next two rows are the test set. Okay, so how can we do that? Okay, so this is a way to do it. We can uh, okay, so okay, so let's see. Okay, so before I tell you that, let's see how to actually take out a subset from this set. I mean, let's say you want just first row. Okay, so how to get that? Okay, so let's see. Print. Okay, let's see if I run this, what I'm going to get. Notice that if I put 0 over here, okay, comma, so basically use these brackets, okay, the square brackets. This is basically the row number. Okay, so 0 is a no row number, and you want all columns. Okay, so you can put this column sign. Okay, and then when you do this, you'll get the first row. Okay, so let's say if you just want if you just want the uh, second column and the second and the third column, so basically if you want just 1 comma 2, okay, then how will you get that? Well, just let's just try this. Okay, 1 2 3. Okay, if you run this, you will get 1 comma 2. Let's check that. exactly. Okay, so I mean, have you understood how to get a specific row and some subset of it? You can. So let's say if you want 9, 10, 1, 2. Okay, so basically, which means that this block, this is what you're interested in. Okay, which is basically the third row and the fourth row, and first column and the second column. Sorry, second column and the third column. Okay, so how to get that? Well, you can do something like this. Okay, so this is the second, this is 0, 1, 2. So third row, fourth row. So if it is a third row, fourth row, then you have to put 2, okay, to 5. Okay, is that fine? So third row. So third row, as I've told you, indexing start from 0 in Python. So this is 0, 1, 2. Okay, and then up to 5, 5 not included. So that means 2 to 2, 3, 4. Okay, is that fine? Is that okay?
Yes, Professor.
Okay. Just a minute. Sorry, up to 4. Sorry about that. Yeah, up to 4. So 4 not included. 0, 1, 2, 3, 4. So that's this is going to be the fourth row, right? Fourth as in if you start from the 0. So 2 to 4 and 1 to 3. Okay. So this will give you 9, 10, 1, 2. This particular block. Okay. So let's run this. Okay. So now you know actually how to split the data set into I mean, now once you know how to actually slice, or basically how to uh, capture a subset of the data set, then it's now very easy to actually split it. So let's do that. Okay. So what you can do is you can call these data sets. So suppose you want to create a split from third. Okay. So okay. So when I say 2 to 4, okay, so 0, 1, 2, okay, 2 is included, okay, 3, 4, 4 is not included. Is that okay, Gaurav?
Yes, Professor. Got it.
Okay. So suppose I want the first three rows, in the training set, and the remaining two rows in the test data set. Okay. So how can we do this? Well, yeah, first end is closed and second end is open. Yeah. Okay. Train test equal to, okay, data set. Okay. So it's just the same thing. Okay. No difference at all. So this is actually another way in which you can define uh, two variables simultaneously. You can just, instead of writing train equal to this, test equal to this, you can just put train comma test equal to whatever train is equal to will be the first thing, whatever test is equal to will be the second thing, separated by commas. Okay, so that ways you are able to define both of them at the same time, so you can do that. Okay, there's no problem. Okay, so I want the first three rows, okay, to be my training set. So what I can do is I can put, you know, so this is another way, either you can put 0 is to split, okay, or you can put, just, is to split. Okay, so that is just going to be the same thing. Okay, since I want all the columns, so I'll just put the column sign over here. Okay, so, and then what is my testing data? So testing data is split onwards. Everything, everything split onwards is my testing data. Okay, is that fine? Okay, now if you want to print the training data, you can actually print train. Okay, and you can see the desired output. Okay, and if you want to print the test data, you can also do that and see the desired output. Is this fine? Is that okay?
Yes, Professor.
Okay. Uh, so sometimes you have one big array and you want to reshape it and convert it into a matrix. Okay, that is also something that you can do. In using NumPy. Okay, so let me tell you that. Okay, so let's just create some another data set, which is okay. So np dot arrange from 1 to 12. Okay, let's see. Okay, so it has 11. Okay, let's just not take a prime number. Okay, let's take um, okay, fine. So now it has 1 to 12. Okay, now what I want to do is I want to create a 3 by 4 matrix. Okay, with these numbers. Okay, so this is how we can do it. Okay, can you see this? Okay, so like it's a way to reshape your array into some other shape. So sometimes it is kind of a very useful function. Okay, uh, by the way, you know this is not going to even if you reshape it, it is not going to override data set. Okay, it is just going to create a new array. So if you want that your data set should be overwritten by this reshaped then you have to say that data set is equal to data set dot reshape. Okay, now if you print data set, okay, it will be overwritten by this reshaped data set. Okay, is that clear? Is that clear?
Clear. Yes, Professor.
Okay, okay. Mhm. Okay, so let's see. Mm, okay, now suppose you have this data set. Okay, and you want to find the sum uh, of well, of you can also find the sum of the entire data set. That's also true. But let's say you are only interested in the sum of the elements in each of the columns. Okay, so let's say you are interested in this sum, this sum, this sum, and this sum. Okay, so how do you get that? Okay, so let's first try this np.sum. Okay, now if I just put this, okay, then it's just going to give me the sum of the entire data set. Okay, which is you can check this that it is 78. Okay, so if you just sum all these, so you should get 12 into 13 by 2. Okay, which is 78. Okay, but let's say I'm interested in some of the columns. Okay, uh, like each column sum. Okay, so how can we do that? Okay, if you want, you can read the documentation for NumPy. Okay, that's one thing. Otherwise, if you just put one over here, it's just gonna give you the sum of the columns. Okay, let's just run this and check. Okay, well, oh, sorry about that. This is going to give you the sum of the rows. Okay, not the columns. Okay, just put zero over here. Okay, I think that's just going to give you. Okay, okay. So if you put zero over here, that's just going to give you the sum column sums. Okay, if you put one over here, that will give you the row sums. Is that fine? Like this will give you the row sums, and zero will give you the column sums. Is that clear? Okay, similarly you can do np.mean. Okay, that's just going to give you the means. Okay, the sum, like uh, it's just going to give you the mean of the columns or mean of the rows. If you want, you can try that as well. So np.mean. Okay, let's just do that. Okay, okay, so if you see over here, it's 5 is the mean of this, 6 is the mean of this, 7 is the mean of this, and 8 is the mean of this. Okay. Is that fine?
Yes, Professor.
Okay, okay. Okay, now let's do something interesting. Okay, so you know how to generate random numbers from uh, uniform distribution, right? Okay, so we have done that, right? Let's see. So using the random library, we have done that. Shreyas, if you want to ask questions, don't post the question privately, because otherwise, nobody will know what are you asking me. Okay, so just post your question to everyone so that everyone can see what your question is. So basically, Shreyas is asking, is there a function for sum of diagonal elements? Okay, so sum of diagonal elements is known as trace. Okay, well, just one diagonal. Okay, I'm not talking about all the diagonals. I'm just talking about the diagonal like that. So I'm sure there is a function. Okay, let me just try this. np. Okay, let's first create a square matrix. Okay, uh, and then just see. Okay, so a equals to np dot array 1 2 3 4 dot reshape 2 by 2. Okay, print a. Okay, you can see this is a. Okay, Now, so what is np.trace of A? Okay, this trace, is actually the sum of the diagonal. So it is just going to sum this diagonal, okay, not this. Okay, so if you want, you can just check this quickly. Just change this, okay, and let's run this now. Okay, so now you have 1 plus 4 is 5, 5 plus 3 is 8. So obviously you should get 5 only, because the trace is basically some of these diagonals. Is that fine?
Yes, Professor.
Okay, okay, Shreyas. Yeah. Okay, so let's do something, as I've said, let's do something interesting, where we are going to just draw numbers from uniform distribution. Okay. Uh, okay, let me write what are we doing. Okay, so I'm sure NumPy also has a way to generate numbers from uniform distribution. Okay, let me just see if that is there. Otherwise, I'll use a random library. Okay, so we always have an option to use a random library, right? So, okay, okay, so NumPy also, you can actually use NumPy also to generate random numbers from, for example, normal distribution. If you want to do that from normal distribution, you can put np.random.randn. Okay, so this is is a way to do it. So let me see. There must be some way to do it from. Okay, yeah. So you can actually use numpy.random.random. That is okay. So that is the way to generate random numbers from uniform distribution. Let's try this out. Okay. Okay. So what I'll do is I'll just generate 100 data points, from uniform 0 1 distribution. So np dot random dot random n. Okay, let's put this in, x. Let's call this x, and let's print x. Okay, fine. So we are able to do it. Okay, is that fine? Okay.
Yes,
Okay.
yes,
Now if
Professor.
I okay now uh, if I plot a kind of histogram plot, for this, do you agree it's just going to be more or less like a uniform thing, from 0 to 1, right? We have already seen that. Yes.
Right.
Okay, so it's kind of like uniform thing from 0 to 1, right? I mean, you can see that this is just more or less the same heights. The frequency of in each bin is kind of similar. Okay, and the reason is because we are drawing from uniform 0 1 distribution. Okay, so let's do one slightly different exercise. Let's do this. That uh, let me just take this x, okay, and reshape it. Okay, so x dot reshape. So let x be x dot reshape. Okay, so what I'm going to do is, you know, I want n by 2 rows, okay, and 2 columns. Is that fine?
Right.
Okay, and now what I'll do is, I'll do so we have n by 2 rows, so I want to do uh, so I want to sum each row. Okay, so since we have n by 2 rows, so basically if I sum each row, okay, so let's see, or let me take np dot mean. Okay, a mean of each row. Let's call this m. Okay, okay, before I plot it, let me just comment it out. How many elements will m have? Like, what is the shape of m?
N elements, Professor.
N? Are you sure? M. Okay, so how many elements will m have?
N by 2.
N by 2. That's right. Okay, let's run this. Let's check. Oh, is there a problem? Hmm.
It is
Okay.
because n by 2 gives float.
Yeah, n by 2 actually, it is not automatically taken as an integer. So that's the reason. Okay, so let's just do this int n by 2. Okay, then it's just going to work fine. Okay, let's run this. Okay. Just always get confused with this 0 1. Okay, so I think this is what's going to work. Okay, just okay. Now this is fine. Okay, is that fine? So what I'm doing is, I've just reshaped it. It has 5,000 rows and 2 columns. Okay, and what you're doing is basically, for each row, you're just summing the entries. Okay, so you get, so you're summing basically for each row. We have 2 elements in each row. Okay, and you just sum them and you divide it by 2. Okay, so because that's what you're doing, np.mean. Okay, so what will be the shape of it? It's just going to be 5,000. Okay, uh, that's what you're getting over here. Okay, now let me ask you this. What do you think? What kind of shape can you expect if I plot the histogram? Is this going to be uniform 0 1? Do you want to see the elements of m? Okay, before I plot the shape, let's just see the elements. Okay, uh so let's not see all 5,000 of them. Okay, let's see just 10 of them. Okay, this is fine. Okay, so obviously, these are always going to be numbers between 0 and 1. The reason is because we added numbers between 0 and 1 and then divided them by 2. Okay, so added two numbers between 0 and 1 and then divided by 2, and that is how we got each of these entries. Okay, now the question is, if I plot the histogram, what kind of shape can you expect of these m's?
So, Professor, what does the sum of two uniform distributions give? I'd be happy to say we could use the central limit theorem if the sample size was more than 30 or so. But since we only have two columns over here,
Yeah,
uh,
we just did two, sum of two of them. Okay,
right,
so obviously you cannot apply central limit theorem here. The reason is because we are just adding two observations from uniform distributions.
right.
Okay, so if you're adding two observations from uniform distribution, you will not get a normal distribution, but you will get a triangular distribution. Okay, so let's just see. Okay, now that you have seen this, okay, you can see that this is how it's going to look. Okay, so it's just going to be like kind of a triangular distribution, with the peak at 0.5. Okay, so if you want, you can just increase the bins. So let's say bins is 30. Okay, let's run this. Okay, you can see it's just more or less like triangular. Okay, and if you just increase the number of observations, you will find something like this. Okay, it's not normal distribution, but it is uh, you know uh, but it is like, it's just beginning to uh, tend to normal, like, so if you instead of using 2 n by 2 comma 2, if you would have used n by 10 comma 10, okay, you would have got something which will look like normal. Okay, so let's just try this one. Okay, so I've taken n by 10 over here and 10 over here. Okay, now if you see, you will get kind of a bell-shaped thing. Okay, let's run this. Can you see this?
yes,
Okay, because now you are adding 10 of them. Okay, 10 of the uniform 0 1 random variables, and that's why the shape has started becoming more and more bell-shaped. Okay, so that's because of central limit theorem, precisely. Okay, as you just said. Okay, is this fine?
yes, Professor.
Okay, so let's continue. Okay, of course you can also do something like this. You can actually find dot product of two vectors. Okay, so let's say np dot array. Okay, np dot array 2 comma 3. Okay. Now if you want to figure out the dot product of a and b, you can just use this. Okay, A dot B. That's one way to do it. Okay, another way to do the same thing is np dot A comma B. Okay, whichever way you like, you will get the dot product. Is that fine? Okay. So all of you are aware of what dot product is? So it's 1 into 2 plus 2 into 3. Is this fine?
Yes, Professor.
Okay. Now, if you have an array and you want to multiply every element of an array by a constant, this is how you can do that. Okay. So let's say C is 5. Okay, and you want to multiply every element of A by 5. Okay, then you can just simply use C star A. The multiplication will happen automatically. So like, it's kind of interesting that when you do A star B. Okay, let's just try both of them. Okay, A star B. Okay, let's just print out the results. Okay, so when you do A star B, it is just going to multiply element wise, because A and B both are arrays of the same size, just going to multiply element wise. Okay, and when you do C star A, so C is a constant. So what it's going to do is it's going to automatically think, like, it's just going to automatically take this operation star as multiplying this 5 by each element of A. Okay, so yeah, so it's actually very convenient in that sense, because this is precisely the kind of operation that we'll be more or less interested in whenever we'll just do the multiplication. Okay, so either the constant with every element of the array, or element wise multiplication operation. So that's kind of very convenient. Okay, so you can okay, okay. So let me talk about norms also. So suppose you have a vector and you want to actually figure out the uh, you know kind of dot product of the vector with itself, something like that. Okay, so of course you can do A dot A, and then do it, but let me give you some inbuilt functions which can give you norms. Okay, so let me first define the two norms. Okay, so one norm that I'm interested in is this one. Okay, okay, so one is this one. Okay, so it is so basically, you can just imagine that you have A, which is a vector A1, A2, AN. Okay, and then what is this A1 norm? What is this L1 norm? So you call it L1 norm actually. So what is this L1 norm? It is absolute value of A1 plus absolute value of A2 plus absolute value of an. Okay. And another norm that I'm interested in is L2 norm, which is uh, square root of a1 square plus a2 square plus an square. Okay. Okay. So basically, these are the two norms that I'm interested in. Okay. So is there an inbuilt function which does that? So yes, there are. Okay. So let me define some a. Okay, and then we'll figure out. Oh, we already have a, so we can just use this a and figure out its L1 and L2 norm. Okay, so by so there is this in NumPy, you have this library, okay, and LINALG. Okay, so if you want, you can call it linear algebra. Okay, so it's a linear algebra library in NumPy. Okay, that you can use. Okay, to figure out the norms. Okay, np.linalg.norm. Okay, and then you just put a1. So if you put a1, it is just going to print out the L1 norm of A. Okay. So notice that A is 1, 2. So if A is 1, 2, then we should get 1 plus 2, which is 3. Okay. So because this absolute value of 1 is 1, absolute value of 2 is 2. And if you add them up, you should get 3. Let's run this and see what are we getting. That's exactly what we are. What are we going to get? Okay. And if you want L2 norm, so L2 is actually default. So if you want, you can put a comma 2. Otherwise, if even if you don't put that, it will automatically give you the L2 norm. Okay, so what can we expect? So it should be 1 square plus 2 square, which is 5. So we should get something like square root of 5. Okay, so let's run this. Okay, and this is close to square root of, I mean, this just basically. Okay, is that fine?
Yes, Professor.
Okay. Okay, so we can also figure out the inverse of a matrix, determinant of a matrix, uh, and we have just done trace. We can figure out the trace. So let's do all these. Okay, let's just try them out. Okay, so let me create some square matrix. Okay, so let's say A is okay. So we have this square matrix minus 1 0, sorry, 1 0 minus 2 5. Okay, so what is the determinant? Determinant is of course 5, right? Okay, so let's just see how we can use NumPy to determine the determinant. Okay, so again, you can use linear algebra library within NumPy to actually determine the determinant. So np dot alg, okay, dot det, okay. Let's print that out. So you can see it's 5, okay. And then you can also if you want to determine the inverse, okay, you can also do that. Okay, just again use the same library, okay, and instead of det use inv, okay, and let's run this. Okay, so this is the inverse. Is that okay? Okay, if you want to do matrix multiplication, that is also something that you can do in Python. Okay, uh, so let's try this out. Okay, so we have this a, right? Okay, so let's multiply it by inverse of a. So what do you think you will get if you multiply a and inverse of a?
Identity matrix.
Right.
You should get identity matrix, right? So let's just do that. A. So this is how you can do it. Okay, a at the rate. So this will be the matrix multiplication. Okay, so I mean you cannot use star, because if you use star, then it is just going to do the element wise multiplication, but that's not matrix multiplication, right? So we can, so there is this inbuilt functionality. You can use at the rate, which is going to do the matrix multiplication. Okay, let's run this. Okay, you can see that it is an identity matrix which is expected, right? Yes.
Right, Professor.
Okay, you can also figure out the rank of a matrix. So what is the rank of a matrix? It's basically, number of independent columns. Okay, so you can actually figure that out. You can also figure that out using this NumPy library. Okay, linear algebra library. Okay, so there's something called matrix underscore rank, which you can just apply and you'll get it. So of course, this is a this particular square matrix is a full rank matrix. The reason is because its determinant is non-zero. So clearly, if I apply matrix underscore rank to A, we should get 2. Okay, so let's run this and check. Okay, is that fine?
Yes, Professor.
Okay. Okay, so let's look at some more methods that are there in NumPy, which are kind of useful. So let's create an array. Okay, so let's say np dot let's say 4 2 3 1. Okay, okay. So we have an array which is if you want you can just check, print a. Okay, so what we can do is we can actually sort. So if this is in this order, we can actually sort this and just and then print a. Okay, okay, let's run this. Okay, you can see that once you want to apply sort, it is going to create, it is just basically going to sort a, and so it is not going to create a new vector here. It is just going to sort the original vector. Okay, And now, when you print a, it is the sorted sorted form of a. Okay, is that fine? So if you want to figure out, the max value in a, you can actually put a dot max. Okay, that's just going to return you. You can see 4 is the maximum value or in a, so that's why, if you put a dot max, it's just going to give you the maximum value in a. Similarly, you can print out the minimum value in a by a dot min. Okay, if you want to okay, if you want basically the index of where is the highest element in a, then you can actually use argmax. Okay, so you must have seen argmax already, when I gave you that alternative way of writing the utility maximization uh, definition, sorry, utility maximization code, which is there on Piazza. So there also we have used argmax to solve the utility maximization problem. Let me just tell you what exactly it does. So notice that now A is this. Okay, so where is the maximum over here? It's basically at the third index, right? 0, 1, 2, 3. So if I put, okay, if I print a dot argmax, it should give me the element, it should give me the index of where the maximizer is located. Okay, so a dot argmax is 3. Is that fine? Okay.
Yes, of course.
uh, okay, you also have other functions which are actually kind of very useful. You can use cumulative sum function. Okay, so what is cumulative sum function? So cumulative sum function will do something like this. It is going to return you a vector of the same size as the input. Okay, in this case, if we take this as our input, then this will give us, so if I do the cumulative sum, it will give me 1. Okay, the first entry will be 1, the second entry will be 3, the third entry will be 6, and the fourth entry will be 10. Okay, so let's run that. Print a dot cumulative sum. Okay, okay, let's run this. Okay, so as expected, we got this. Is that fine? Similarly, you also have cumulative product. Okay, so if you want, you can try that out as well. Okay, print a dot cumprod. Okay, let's run this. Okay, and you can see that it's just 1. The second entry is 1 into 2, 2. Third entry is 1 into 2 into 3, which is 6. Basically, it is just going to give you, in this case, 1 factorial, 2 factorial, 3 factorial, because our numbers are 1, 2, 3, 4. Okay, is that fine? Okay.
Yes, Professor.
Okay, you can also, again, NumPy also has a way to, by the way, I'm using a dot min, sometimes I'm using np dot min, so let me just make this doubt also clear. Okay, so a dot max, there is an alternative way of writing a dot max. Okay, you can just put np dot max a, it's the same thing, it's just it's I would say kind of faster, so that's why I do it like this. But if you want to stick to the original way, that okay, we are importing some functionality from NumPy, you can also use this. Okay, so max is kind of an inbuilt function in NumPy. So so np dot max, and in bracket if you put a, it's just going to give you the same result as you get with a dot max. Okay, so a dot max is just so when you do this, it's the same thing as np dot max a. Okay, so whichever way you like. Similarly for the other functions also, this is also np dot min a. Okay, this is also np dot argmax a. Okay, and this is also np dot cumulative sum a. Okay, similarly this is also np dot cumulative product a. So whichever way you like. Okay, either you can put a in the bracket and you put np over here, or you put a directly over here, because it's a numpy object, so it will automatically will be treated like a numpy object. Okay, so is that fine? Okay. Okay, so you can actually figure out the variance. Okay, so we have this. So if you want to figure out the variance of this, you can actually use a dot var. Okay, and you can print out, and that's just going to give you the variance of the elements in a. Okay, so in this case the variance is 1.25. If you want, you can check this also. So you already know how to figure out the mean. Okay, a dot mean. Okay, so let's quickly see. So a dot mean is 2.5. Okay, so what you can do is you can just subtract a dot mean from a, right? I mean, that's how you find the variance, right? Okay, and then take the square of it. Okay, and then take the sum. Okay, and let's run this. Okay, this should give you the variance. Sorry, you have to also divide it by the number of sorry. Okay, can you see this? Okay, I mean, you're just gonna get the same thing. Okay, is this fine?
Yes, Professor.
Okay, yeah. So if you want to do the standard deviation, you can use think std. Okay, okay, that's the standard deviation. And if you want to check what is the standard deviation over, like, I mean, of course, that's a square root. So uh, see that you'll get the same number. Okay, is that fine? Okay. Okay, so you can actually also apply functions on arrays. Okay, so let's see how. Okay, so let me create okay, so let me create another another vector. Okay, so np.array. Okay, and put some list in it. Okay, so 0 comma 1 comma np.py by 2. Okay, so this is just pi by 2. Okay, and then let's say np.py. Okay, and this is just pi. Okay, let's print z. Let's see. Okay, so this is pi by 2. Okay, this is 0, this is 1. Okay, now let's apply a sine function to it. Okay, so again, the sine function, which is also an inbuilt function in NumPy. Okay, so let's see np.sine z. Okay, let's print that out. Okay, so you can see that you know so this is close to 0. Okay, so sine pi is 0. So when you see e is minus 16, so this is actually this number multiplied by 10 to the power minus 16, which is actually close to 0. Okay, so we don't have to worry about it. Okay, and then this is pi by 2, so sine pi by 2 we know is 1, so this is also, you can see, is close to 1. Okay, and sine 0 is 0, so this is also close to 0. Is that fine? Okay, so basically, you just take one function, you can apply it to the entire vector. Okay, which is also very, very useful functionality. Okay, so you can also there is another function called round. Okay, which is just going to give you the so basically it's just going to round to one decimal place or two decimal place, the numbers that you are so like for example here, we have numbers in many decimal places. So if you just round it, it's just going to round it to the number of decimal places that you're interested in. Okay, so let's try that out as well. Okay, print np.round. Okay, np.sine z. So I want to round these numbers. Okay, let's say up to two decimal places. Okay, and let's run this. Okay, so now you can see, this is 1, this is 0, this is 0, and sine 1 is basically 0.84. Okay. Is that fine? Is that fine?
Yes, Professor.
Yes, Professor.
Okay, okay. Okay, now suppose I define my own function. Okay, you know how to define your own function, right? I mean, we have done that several times. Suppose I define my own function and I want to apply that function to a NumPy array. Will I be able to, get this same functionality? Like, will I be able to actually, apply to every element, the function that I've just created, okay, to a NumPy array? Okay, let's try that out. Okay, so I mean, of course, np.sine is an inbuilt function in NumPy, so I'm able to actually apply it to every element. Okay, and create a new array, which consists of the values that sine function takes at each of these elements. Okay, but will I be able to do the same thing with the function that I define myself? So that is something that we would want to check. Okay, so let me create some function. Let me first create some array. Okay, np dot array. Let's say minus 1, 2, 3, 9. Okay, okay. Now what I'm going to do is I'll create a function that takes value. I'll create a function, that takes one input and takes value 1 if that input is greater than 2 and 0 otherwise. Okay, so define f of x. So if x is greater than 2, then return 1, else return 0. Is that okay? So I've created this function. Okay, now let me see if I can just take this function f and apply it to z directly. So can I do that? I mean, I was able to do with np.sine, but can I do this with f? So let's just try that out. Print fz. Well, there is an error. So you cannot do that. You know, you cannot just take your own function and apply it to an array, at least not like this. Okay. So is there a way to do it? So there is a way actually. You can there is a function called vectorize, okay, in NumPy, which can actually do the same thing for you. Okay, so let's do that. Okay, so what you can do is this. You can overwrite f with the vectorized version, okay, of f. So f is equal to np.vectorize f, and now you can just do the same thing. Okay, now there'll be no error. Okay, let's run this, and you can see that this is exactly what you were hoping, because this should be 0 because this is less than or equal to 2. This is also less than or equal to, so this should be 0. This is greater than 2, so this should be 1. This is greater than 2, so this also should be greater than 1. Is that fine? Okay, so if you have your own function, okay, which takes a single input, and you want to apply that particular function to every element of the array, so of course there is a way to do it. You can write a loop also, but of course this is much better. You can just do the np.vectorize, and then it's just going to apply that particular function to every every point in the in the vector. Okay, is that fine? Is that okay?
Yes, Professor.
Okay. Okay, so remember we did Booleans, okay? So we can actually also compare arrays, using Booleans, okay? So let's just create two arrays, and okay. Now let's just put z equal to y. So this will actually create again an array of booleans. Okay, so if I put z equal to y, it is just going to create it is just going to check element wise, whether the first element of z is equal to the second element of first element of z is equal to the first element of y or not, second element of z is equal to the second element of y or not. So it's just going to do this uh, this comparison element wise, okay, and create an array. Okay, so let's just check that. So you can see that we got true. Okay, so what that means is 2 is equal to 2, 3 is equal to 3. Okay, and let's say if I just make this 1 and make this 0, and if I run this again, okay, it will create a vector of size 3, you know and it should be true false. Okay, let's run this. Is that fine? Is that okay?
Yes, Professor, that's fine.
Yeah, okay. Now this is actually kind of very useful, because sometimes you just want those entries from a particular, so that subset of z for which a particular condition is true, and you don't want the others. Okay, so you can actually use this to also subset an array. Okay, so let's just check this. Okay, z equal to y. Okay, let's see. So if I so what I've done is basically I've taken this vector z equal to y and put them in these brackets. Okay, so basically it's just going to put so what we are doing is basically z. So we want those entries of z for which z equal to y holds. Let's print that out. Let's see what we get. Okay, you can see that it is just the first two entries. So this is a very nice way of subsetting a vector based on a certain condition that you want to be true. Okay, so of course this is actually very useful in simulations, finding probabilities. When you just want a particular condition to be satisfied, you just want to subset that out. So all that is extremely helpful. Okay, is that fine? Okay. So you can actually also solve a system of equations in using NumPy. Okay, so far we are just looking at NumPy. It has actually a lot of functions, and this is so if you just check the document, you'll find a lot more. Okay, I mean it's just I'm just trying to give you the ones that we'll be using more often, but of course later on if we'll use something else, I'll let you know about that as well. Okay, so. Uh, Okay, so suppose you want to solve a system of equations, okay, and how can we do that using NumPy? Okay, uh, so what is the system of equations? So basically, a system of equations can be written as ax equal to b, right? Okay, and you want to solve for x. Okay, so this is the system of equation, and you want to solve for x. Okay, so what I'll do is I'll just create a matrix A. Okay, I'll just give some matrix A and then some vector B. Okay, and then we'll try and figure out what value, what vector x solves this equality ax equal to b. Okay, of course you can also do it in this way, that you can just find A inverse, okay, and then multiply it by b. That's one way to do it. We already know how to do the matrix multiplication. We also know how to find the A inverse. Okay, so we can also use that, but then we can also do it directly. I mean there is an inbuilt function in linear algebra library of NumPy, which can help us accomplish it. Okay, so let me define A. Okay, so let's say A is this. Okay, so I'll put a list of three lists. Okay, so those are three rows. Okay, so let's say 3 comma 2 comma 0. Okay, and then 1 comma minus 1 comma 0. Okay, and then finally let's put 0 comma 5 comma 1. Okay, so I have this matrix A. If you want to check, print A. Let's run this. Okay, now let me create B. Okay, so B is np.array. Okay, let's say B is 2 comma 4 comma minus 1. Okay, okay, so I have A and I have B. Okay, now I want to solve it. I want to solve this ax equal to b for x. So how can we use linear algebra library? So basically this is how you can do it. Okay, so x will be np.linalg.solve. Okay, and you put a comma b in the brackets. Okay, and then you can print x. Okay, so you see that the values are 2 comma minus 2 comma 9. Okay, now if you want to quickly check your answer, okay, you can just do something like this. You can do the matrix multiplication of a with x. Okay, you can do the matrix multiplication of a with x. So there are two ways to do it. You can do a at the rate x. That's one way. Okay. The other is you can do a also dot product. Dot product is also something that will give you the same thing. A dot dot x. Okay, let's print that out. Okay, and that's exactly the value of b, right? So this is a way to quickly check your answer. Uh, that this is indeed the solution to ax equal to b, because a times x is actually b. Is that fine? Is that fine?
Yes, Professor.
Okay. Okay, now let's look at another library, SciPy. Of course, we are not done yet. We'll be talking about eigenvalues, eigenvectors, and all that stuff as well. But before that, let's also look at SciPy. Okay, so SciPy again, is just full of a lot of useful stuff. It also has again, it also has a linear algebra library. If you want to check that out. So okay, so anyways, let's look at this library today. Okay, statistics. So this is also in SciPy. Then there are a lot of discrete statistical distribution, continuous statistical distributions. You can generate random numbers from any distribution of your choice. Okay, you can use so like for example, if you want to generate random numbers from some discrete distribution, okay, you can click on this. Okay, okay, and then let's say you want to generate random numbers from geometric distribution, so you can just click on this. Okay, so this implementation is given over here. So if you click on this, you will find the examples of how to implement it. Okay, uh, so let's maybe look at one or two of these. Okay, and then I'll take your doubts. If you have any questions, you can ask. Okay. Okay, so do you want me to use geometric, or do you want me to do some other distribution? A binomial, Poisson, geometric, negative binomial, hypergeometric, or let's just do geometric. Okay, so all of you are aware of geometric distribution, right? Yes.
Yes, Professor.
Okay, so basically, it is it's basically, it's given over here. What is the definition that we need to use? A geometric random variable with parameter p can be defined as number of trials required to obtain a success, where the probability of success in each trial is p. Okay, of course, it's not written over here. We are also assuming that these trials are independent. Okay, so these are independent trials. So number of trials required to obtain a success, where each probability of success of each trial is p. Okay, so the distribution of that is geometric. Okay, like number of trials. Okay, is a geometric random variable. Okay, so suppose I generate a random number from a geometric distribution. Okay, so this is what we can do. So from SciPy.stats, we can import geom. Okay, so this is the command that we can use. Okay, so let's just copy this. Okay, where is Okay, so we are importing geom from SciPy.stats. Now, what is the advantage of this? You could have also imported, SciPy as SP. That is also fine. That will also work. Okay, you can also say import SciPy as SP. Now, if you do this, then if you want to use geom, so suppose you don't do this. Okay. Now, if you want to use this geom functionality or geom library within the SciPy.stats, then you have to do something like this: sp.stats.geom dot whatever. Okay, so I mean so whenever you want to use the geom functionality, you have to use something like this: sp.stats.geom and so on and so forth. Okay, now of course a better way to do that is just simply say that from SciPy.stats just import geom. Now you'll not be able to use the entire SciPy library, because you have just imported geom library from within SciPy.stats. But the good thing is that now whenever you want to use anything from geom library, you just have to put geom dot whatever. Okay, you don't have to put SciPy.stats.geom because you have just imported geom from it. Okay, so is that fine? Okay, I mean you can also do something like this as g, but geom in itself is very short, so you don't have to import it as some other letter, like for SciPy, used SP, for NumPy used as NP. You can also do something for geom as well, but geom in itself is short, and it's also conveying the message that this is what you're doing. So I think it's better if you just import it in this way. Okay. Okay, now we have this PMF CDS. So if you see, all these methods are given over here, associated with this particular module. These are the methods. So you can actually use RVS to generate random numbers, from geometric distribution. Okay, you can use PMF to figure out the probability mass function. Okay, you can use CDF to figure out the cumulative distribution function, and so on and so forth. I mean, you can figure out PPF for it's a percent point function. You can also call it inverse of the CDF, okay, or a percentile function. Okay, and you also have stats, where we can figure out the mean, the variance, the skewness, the kurtosis associated with the distribution. Okay, is that fine? So let's maybe try some of these. Okay, let's say let's use RVS first. Okay, sorry. Okay, so P equal to, let's say, half. Okay, and size is 10. Okay, let's just call this X. Okay, let's print out X. Okay, so these are basically 10 numbers which are generated from geometric half random variable. Is that fine?
So could you explain the P of again?
Yeah, so P is basically, I think just so P is basically, uh, the parameter associated with the geometric random variable. Okay, so if the probability of success in each trial is half, then what is the total number of trials until you succeed? Okay, so until you succeed in these successive uh, trials. So okay, let's to give you an example. Okay, suppose you keep tossing a fair coin till you get a heads. Okay, you can imagine this experiment. Okay, keep tossing a fair coin till you get a heads. Now the number of tosses till you get a heads is a random variable, right? It's a geometric half random variable. Yes.
Got it.
Okay, so clearly, if you do this experiment once, okay, and rest from this, so this tells you that it took you 3 trials to get the first heads. Okay, if you do this experiment twice, it tells you that when you did this first time, it took you 3 trials to get the heads. When you did it the second time, you got the heads in the first trial itself. Is this fine?
Yes, Professor.
Okay, so that's basically like generating random numbers from a geometric distribution. Okay, okay, let's generate hundreds of them. Okay, maybe 100 of them. Okay, and let's do the same thing. Let's plot the histogram. Okay, you can see that roughly around 50% of them, you got in roughly around 50% of them, you got heads in the first trial itself. Okay, so this is also kind of because of law of large numbers, because if you see the probability of success in each trial is half. So you will be able to get the heads in the first trial itself. The probability of that is half, right? Yes. Okay, so out of these 100 trials, roughly around 50 of them you'll see that you will get success in the first trial itself. Okay, so that is why you see roughly around 50 of them, we just needed one trial to get the heads. Okay, so yeah, I mean that pretty much explains why the geometric distribution is like this. Okay, is this clear? Okay, and if you want the actual PMF, okay, what is the probability mass function, then you can use PMF. Okay, so this is you can use, so let's just quickly do that as well. Okay, so PMF geom.pmf. Okay, and let's print out the for everything from 0 to 10. Okay, let's figure out uh, the PMF for x's between 0 to 10. Okay, so let's say x is np dot arrange from 0 to 10. Okay. Okay, and let's put x over here. Okay, print we have to also supply half, right? I mean, because geom PMF takes the first entry is basically, the x's, the second entry is the p. Okay, so we have to also provide p over here. Okay, so p is 0.5. Okay, let's print that out. Okay, so these are the probabilities. Okay, probability that x takes value 0 is 0. Of course, you need at least one trial. Okay, so if you want, you can just remove that because okay. Probability that a geometric half random variable takes value 1 is 0.5. Probability that geometric half random variable takes value 2 is 0.25, and then this is 0.125, and so on and so forth. Is that okay? Is that okay? Any questions? Do you have any questions? And you can see it's falling, right? I mean, that's exactly the thing that we are observing here as well. I mean, it's also falling over here. It's every time, you just move to a next point, you just multiply it by 0.5, and this is uh, true about geometry. Okay. Is this clear?
It's clear, Professor.
Okay. 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 So similarly, if you want, you can figure out the CDF. For CDF, you just have to use the same thing. Instead of PMF, use the CDF. Uh, so let's just do that. Okay. Okay. Now, if you run this, of course, now in this case, you'll get an increasing uh, sequence of numbers. Okay. The reason is because CDF is always a non-decreasing sequence. Okay. So let's run this. Okay. Well, it's a non-decreasing function. You shouldn't use sequence, but it's just a non-decreasing function. Okay. So it's just the cumulative sum of probabilities of PMF. Okay, this is 0.5, this is 0.75, this is 0.875, and so on and so forth. Is that fine?
Yes, Professor.
Okay. So we know how to generate random numbers from any distribution now. We know how to generate, uh, how to figure out the probability mass function, how to figure out the CDF. We can also use this PPF function to figure out the percentiles. Okay, so what is this PPF? Okay, uh, okay, so let me use a normal distribution. That's just going to make it more clear. Exactly what PPF is. Of course, we can also use this over here, but I think with continuous distributions, you'll be able to relate to it quickly. Okay, so let me. Okay, let's use normal. Okay. Okay, so what again? I'll do something like this. I'll import norm from SciPy.stats. Okay. Okay. So suppose I want to figure out so of course these are all the functionalities. Okay, let's figure out the ppf. Okay, let's use ppf. Okay, norm.ppf. Okay, suppose I want 97.5 percentile. Okay, so I have to also specify the mean and the variance, well, standard deviation, the mean and the standard deviation. So by default the mean is 0, standard deviation is 1. So if you want to use standard normal, we can use standard normal. So this is by default standard normal. So in that case, I don't have to specify anything because by default it is 0, 1. So let's use standard normal itself. Okay. So can you tell me if I do something like this, what value will I get? Okay, let me just show you in picture exactly what are we going to get. So yeah, approximately 2, right? I mean, so basically, what we are doing over here is we are trying to figure out that value of x below which 97.5% of the observations are located. Okay, so so that's basically your percentile, right? So if you have this standard normal distribution, okay, this is standard normal, this is 0, okay, and we are trying to figure out what is this a, such that this area is 0.9975. Okay, so I want this area to be 0.997, sorry, 0.975. Okay, so I'm looking for what value of a gives me this area as 0.975. Have you understood the question? So if you wish, you can call it the inverse of the CDF. This is the inverse of the CDF, right? Okay, CDF will give me 0.975 if I evaluate it at A. Okay, now I'm given the output of the CDF and I'm interested in its input. So that's like finding the inverse of the CDF, right? Okay, so norm.ppf do exactly that. And as Anand just mentioned, you should get a value close to 2, and the reason for that is because roughly around 95% of the uh, of the observations are between -2 and 2 in case of standard normal. So if roughly around 95% are there between -2 and 2, so by symmetry 2.5% is below -2, 2.5% is above 2. So if we just add 2.5%, which is below -2 to 95%, we'll get 97.5%. So you should get a value close to 2. Okay, so that's what we are expecting. Let's just run this and see. Okay, and then this is exactly what we were expecting. It's just close to 2. Is that clear to everyone?
It's clear.
Okay, now if I do something like this, tell me what are we going to get?
0.975.
That's right. Okay, is that fine? Because this is the inverse, so obviously you should get the same thing. Okay, is that clear?
Yes.
Is that fine? Okay. Okay, so now let me take your doubts if you have any, and then I'll continue tomorrow. Okay, so if you have any questions, you can ask. Any questions?
Uh, Professor, actually, I was looking at the utility maximization problem which we done like in the first, second class, and
Yeah.
I didn't get the proximate demand part of it. So could we go over that again, if it's possible?
Okay, sure. Okay, so this one, right?
Professor.
Yeah. So basically, you what you're doing here is this, that you are basically trying to search, for the optimal solution on the budget line. Okay. So what you are doing is, you are writing a kind of an algorithm, which do the following for you. Okay. It will just look at the budget line. Okay. So this is the budget line. This is m by px. This is m by py. Okay. So the algorithm that we have written, okay, over here will do the following. Okay, it's just going to do the following. It's going to start with some guess. Okay, what is your guess solution? Okay, because this is what I want. Eventually I want x star y star, but I'm going to start with something. So suppose my guess is that this is a solution, right? Okay, so I'm starting with this point. Okay, and what is the optimal value of u at this point? It is given by ux star y star, right? Okay, so now what I'm going to do is this. I'm going to just divide this search for the best point into some steps. Okay, into some tiny steps. Okay, that I'm going to take, you know like this. Okay, is that fine? Okay, so I have just divided into some tiny steps that I'm going to take, along this line. So what I can do is this, that at every step, so this is the loop which is going to do that for me. At every step, I'm going to compare, so x star y star will always contain the value which is your current best. Okay, so far, in your search, whichever is your current best, x star y star will contain that value. Okay, which is something which will happen because of this if statement. So if your uc is greater than, so u current is greater than u star, then you replace x star y star by the current values of xy. So like in the first step, when you go over here, you figure out what is the value of x here, what is the value of y here. Okay, and then figure out what is the value of utility at this xy, okay, which is going to give you u current. Okay, and then you compare u current with u star. So if u current is greater than u star, then you replace x star y star by xy and u star by the new x star y star. Okay, and if that is not the case, then you just keep continuing. Okay, so in that case, you don't do anything. So that is why I haven't written else, because you don't do anything, when it is else. Okay, so you just keep updating x and y. So that's something that you anyways do at every step. So basically that's what the code is all about. I mean, you just keep moving. If you get something better than the current best, you replace it by the current best, otherwise you keep moving. Okay, and eventually when you have gone through the entire budget line and you have reached this point, you know when you have reached this point, now you have the best of the entire line. Okay, so best of the entire line will be basically your optimal point, right? I mean, that's your demand. Do you agree?
Yeah, sure, I got it.
Okay, so basically that's the idea, I mean, that's exactly how you implement it in Python.
Thank you.
No problem. Okay, then let's stop here for today. I'll see you tomorrow.